Right, I think it's now recording. Everyone should be in. Let me just go to the chat. People, right. Good. Good morning, good afternoon, good evening, everyone. Thanks for joining us again on our latest webinar, presented by Martin Cuthbert, on the benefits of variable priority flow control valves. Just a few bits of housekeeping before we start. If you can, keep yourself on mute during the presentation, and at the end we'll open it up to questions. If you do have any questions during the session, if you can put them in the chat, and we'll keep an eye on that throughout, either try and answer them during, or we'll answer them at the end, or get you to take off mute and you could ask them yourselves if you so wish. So with that, just before we start or during, if you could just sort of test the chat out and get it going, if you could maybe just put in there where you're from, any thoughts on the session, just to get a gauge of where everyone's from this afternoon. And I think, what else have we got? This will go out, so after the session there'll be the recording that will be sent to you within about half an hour of the recording finishes. So feel free to watch that as a catch up. And I'll say now, but I'll mention at the end, we're planning on some more towards the end of the year, so keep an eye out on LinkedIn and your email, and we'll keep you up to date with the next sessions we're going to do. So with that, hi to people in Florida. I wouldn't mind being in Palm Beach, Florida at the moment, and Netherlands. Hello. So okay, well with that, Martin, I'll hand over to you to get going.
Okay, thank you very much, Sam. Yeah, welcome everybody. Welcome to this webinar on the benefits of variable priority flow control valves. While we will feature WebTech valves in this, we'll also delve a bit into the principles and technologies behind them, and compare the pros and cons of 2- and 3-port flow control valves, and how they've been successfully applied on various mobile machines to improve the performance and simplify the hydraulic circuit. Okay, so we're going to start by introducing you to a company that some of you may know if you've attended some of our recent webinars. We were talking about this very company, Mining and Oilfield Services, back in March. At that time, we were talking about diagnostic testing and preventative and predictive maintenance. Today, we're meeting them and talking about their range of material handling and recycling machinery, and they've also got some road gritters and snow clearance machinery. This is a fictitious company, but a company that we love and know well. And their mission as a company is to provide a safe working environment, be a reliable supplier of choice, and provide innovative solutions. And the company is led by a very able CEO called Lauren, and he has a whole team of managers working for him. And amongst them is Declan, who's a design engineer, and his main responsibility is on upgrading the hydraulics on the mobile machinery they have in their fleet. And so we'll delve straight into why we're meeting Lauren and Declan and Mining and Oilfield Services. And that is that Lauren has been running the company for a long time, is facing some challenges at the moment. Oil price is down, some of the business is down, and he's not making much profit, and he really wants to reduce the overheads. And so his challenge to Declan is how can we reduce our running costs, that will in turn reduce our what can we do about that? So that's the challenge handed down by the CEO to the engineering department, and Declan's being tasked with improving machinery performance and simplifying the designs so they waste less energy. So in Declan's words, that's really, how can I simplify the circuit and make it run better? Where does WebTech come in? Well, we've been around for over 60 years. As I mentioned, we're also manufacturers of measurement solutions, but we also help with mobile and industrial machinery OEMs with control solutions. The applications that we deal with can vary enormously. So you can see some of the examples on the screen there. They could be in the agricultural industry, they could be in the mining machinery industry, construction, or even some on-road applications. And as a manufacturer in this niche, we have to be flexible and adapt our designs to meet the needs of our customers. And to do that, we have a four-step approach to customizing products. And we call that four-step approach Make It Blue. You can see it on the screen now, and the blue stands for the four large letters across the middle there: begin, listen, upgrade, engineer. And really that's our approach to understanding the customer's problem and engineering a better solution for them, often using technology that we already have within our range. And this webinar today is a good example of where we begin with sharing free to access educational material. Listen would be where we're actually sitting with the customer, understanding their challenge, and then we'd move through to upgrading, whether that's providing 3D models, a prototype, or a working sample. And then finally, we would engineer and manufacture the finished product. Okay, so that's where WebTech comes in. So what would we advise Declan when it comes to his particular challenge? So Declan is sat there looking at a catalogue of products, a whole heap of different flow control valves, and he's asking the question, how can I simplify the circuit and make the system run better? So Declan knows quite a lot about the machinery that they have in their fleet. He knows that many of the machines are over 10 years old. Some of the designs are relatively primitive. So he's aware there's quite a lot of opportunities for improvement. And he's broken those down and put them into sort of 6 challenges that he sees on the machines. And the biggest of those is that the systems are running quite hot. And he's aware that that could be down to the fact that he's using a lot of 2-port valves, and he's wondering about whether a 3-port solution might be the preferable solution for him. And so let's just delve into that a bit more and understand why the 2-port solution is causing him some problems. And so on some of the machines, he has really very basic needle valves to control flow. And so in this example here, you can see the conveyor belt with rocks being loaded onto it, driven hydraulically. So if I just get the pointer, we can see here the hydraulic pump. It's driving oil past the relief valve and up through the variable 2-port flow control to the motor and then back to tank. So as we fire up the pump and start driving oil onto the motor, you can see there's a small amount of oil going to the relief valve, but most of the oil in this instance is going to drive the motor, which is turning the conveyor, which at the moment we can see is only lightly loaded. Because this is a needle valve, we've set the flow maybe sort of 3/4 open. It's not doing that much work because there's not much weight on the conveyor, so the motor's not doing too much work. It's got quite a lot of flow going to it. So it's got quite a big pressure drop across the flow control valve and a small amount of oil going to the relief valve. So one of the challenges they've got is that when they want to put more rocks onto the conveyor, then they have this problem that this high flow at the moment, which is making the conveyor move quickly, actually goes down to much slower speed. So we put the heavy load on. The motor is now having to work much harder. So we've got a higher pressure here on the outlet side of the flow control. But what's happened, because there's no compensation here, the needle valve is only providing a small amount of flow, and most of the flow is now going over the relief valve. So what's happened is that the motor is now turning much more slowly, which isn't great from an operator's point of view. When they put more rocks on, it slows down. When the rocks get to the end and then they've got small rocks on, it then speeds back up again. So from a performance point of view, that's pretty rubbish. And we're constantly putting oil over the relief valve. So you've got relatively slow speed. So the first improvement he wants to make is to ensure that the conveyor belt goes at a constant speed, regardless of whether he's got large or small rocks onto the conveyor at any particular moment. And so here he's replaced the needle valve with this symbol here for a pressure compensated flow control. And so he's got a constant flow going to the motor, giving a constant speed on a light load. As he then loads that with heavy rocks, he's still got a constant speed. He's got a constant flow going to the motor. So there's a couple of ways you might do that. You might introduce a fixed ILFC. So this is a factory set flow control. You might choose the flow 10, 20 litres per minute. That's drilled to size and then put into the circuit, and it will always deliver that flow, and it will compensate for changes in pressure. If he wants to be able to vary the speed of the conveyor, he might then put in an adjustable variable flow control, so that he can choose what speed the conveyor goes at, but it still compensates for differences in load and therefore differences in pressure. I know many people are curious about how these valves work, so we just do a section through the valve. That's a section through the variable flow control valve, pressure compensated. So on the left-hand side, we can see the full symbol. So the flow comes in at 1 and goes out at 3. It goes through the variable flow control orifice here. Then we've got the pressure compensation element, comes out 3. And if the flow is reversed, then it can go back through the check valve and out through 1. And so you can see that here. You can see the check valve arrangement at the front here. You can see that there's a poppet moving inside a sleeve here against a spring, which is the pressure compensation element, and the variable flow element is dictated here by this needle coming down into the flow. So the flow comes in, goes through this orifice here into the center of the poppet, and then out the other side. And exactly how large that gap is, and therefore the amount of flow that goes out, is dictated by the difference in pressure between 1 and 2, which is the pressure compensation, and then comes out of 3. And up on the right hand side, as you can see, the symbol that is shown inside the hydraulic system drawings. That's the abbreviated symbol. Okay, hopefully that makes sense. So we now have a solution which is still 2 ports, but it does enable that the belt is always going at a constant speed regardless of load. So that's the main benefit of the pressure compensation. So the application that Declan's looking at is around the grit spreader. So this is a hydraulic motor driven grit spreader. So this is spreading sand and salt onto the road in winter to help de-ice it. There we can see the grit coming out of the back. So we have again circuit here driving hydraulic pump up through the pressure compensated 2-port flow control and driving the motor, which is spreading the grit. The relief valve here teed into the side. So as we then adjust down the grit, effectively reduces the amount of flow through the flow control, and then the excess flow has to go somewhere because this is a fixed displacement pump, and the excess flow is then going over the relief valve. So there is a downside to that if we have a pump that's, let's say, delivering 100 litres, but we're constantly running it at maybe only 20 litres, then we have most of the flow going over the relief valve. Over a period of time, that relief valve will get very hot, and we start to waste a lot of energy because the whole circuit is running at the relief valve pressure, and 80 litres of it are going straight to tank. So Declan's particularly interested in that because clearly something heating up is a waste of energy, and if he can use that energy better or save that energy completely, then that would be a reduction in the amount of energy being used inside the system. For a diesel engine device, that's then less diesel burnt, which is then the very savings that has tasked him with to reduce the running costs of the machinery. So he's looking for heat, and by focusing on that, he thinks, right, well, there's got to be a better solution there. And at that point, he starts looking at 3-port flow controls. So what we have here is a section through a variable priority flow divider. You can see a picture of it on the top right-hand side and the symbol on the bottom right. And so in this example, the flow comes in the red here. It goes straight across the gallery here, round the spool, and goes through this orifice here, which is set by this needle valve, through the top gallery, and goes out of the priority flow port. And as you can see, all the flow is coming in here, and all the flow is going out of here. So 100% of the inlet flow is going to priority, and here none of it is going to the bypass port. If the flow wanted to be reduced, then the needle comes down, surface closes off. At this point, this spool in the middle then moves over to the left. Let's go back and see that a bit more clearly. There it's one position. See now that the spool's moved over, and some of the flow is now going into the bypass port. So this is the opportunity here for the operator to control the amount of flow. If the priority port is driving a motor, how much of it is going to the motor and how much of it is going to bypass. In addition, this spool on the spring is also compensating for changes in pressure. So the priority flow, and the clue's in the name, priority is always given to the flow coming out of this port. So if we look at that example again on the gritter, so we've still got the same hydraulic pump, still got the same pressure relief valve, but now we're going into a 3-port valve. The priority flow is going to drive the motor, which is turning the gritter, and the bypass flow is going back to tank and teed into the output from the relief valve. The advantage now is that the pressure here on the inlet side to the flow control is the load pressure plus about 8 bar. And 8 bar is a typical flow if you're pushing about sort of 70 litres through about 190 litre valve. Sorry, you're having 70 litres of priority flow on a 190 litre valve. If we then look at that from the point of view of how much pressure variation have we got in the circuit? So, over time, if the pressure varies really very marginally, and you're often running very close to the relief valve pressure, then that may be a reasonable solution for a 2-port valve, because we know that as soon as you have excess flow on a 2-port valve, and that's going to be pushed over the relief valve. So if there's a big difference between the operating pressure and the relief valve pressure, then that's where there's all the wasted energy. So in this particular example now on the right, you can see there's big swings in pressure. So pressure goes from very low right up to relief valve pressure and back down again. So in this instance, priority flow control can offer a massive saving in energy. Because this difference here on a 2-port valve would be wasted power that would be forced over the relief valve and just be turned into heat. So if we look on a 3-port valve, on the right-hand side, you can see that the pressure profile is changing, but the only wasted energy is what's going into a pressure drop across the valve. In this case, it's the 8 bar on top of each of these little spikes here, this little hatched in area. And so Declan's quite happy with that, because that suddenly shows to him that there's an opportunity here for some of the applications where they've got big swings in pressure to actually save a whole load of energy, which otherwise was being turned into heat. And that has lots of other implications. So not only can you reduce the amount of diesel he's burning, so it's calculated for a 100 litre per minute pump, every 10 bar saving of pressure could save approximately 1,000 litres of diesel per year. And if you prefer to have that in an imperial, then 26-gallon pump, every 145 psi saving of pressure could save roughly 265 gallons of diesel per year. So that's one side of it. The other thing is that heat doesn't just evaporate into the atmosphere, it also goes into the oil. And before you know it, you're also having to put a cooler on to go and take the heat back out again. And so there's an opportunity there to simplify the circuit and take some of the cooling out of the circuit, for the simple reason that the heat isn't going in the first place. So the next question for Declan is, well, which valve is appropriate? This particular range has 3 different models in it. So the VFD 50, sized in litres, so that's a 50 litre unit, the VFD 120, 120 litre unit, so a 32 gallon, and the VFD 190. And you can see that the VFD 50 is rated to 250 bar, and the other 2 are rated up to 420 bar. So that's quite an in-depth look at why the system's running hot, but probably the most important reason or challenge that Declan has. But it's not the only challenge that Declan has. He has 5 other challenges, and the next on his list is that he sees the opportunity to try and simplify the circuit. So as we saw in all of those examples, there was always a relief valve in the circuit, and he wants to make sure that he has a relief valve close to his motor. But also, is there an opportunity for him to bring the relief valve into the flow control? So he was very interested to see that there is a variable priority flow divider with a relief valve. You notice, for the eagle eye, you notice that this casting here is a bit deeper, and inside this lower part here is then this relief valve, which relieves from priority to bypass. And by having that function in there, it's an opportunity on some circuits to then say, okay, I can do away with a separate relief valve and just build it into one valve, which from the point of view of retrofitting this into certain machines makes it an awful lot easier, because it then just has to pipe in one unit rather than putting in a sort of spaghetti junction of multiple valves. Okay, so the next problem that's been reported, or challenge that's been reported to Declan by some of the operators, is that all well and good that the machine delivers the same flow, but there are also sometimes other performance characteristics that are important. So if we look at this graph here of, let me just interpret this for everybody. So we've got the input flow here in blue. Here you can see that, and you can see that the priority port, when it's loaded, suddenly the pressure shoots up on it, and then it's unloaded and goes back down again. And when the priority port pressure is loaded, then that pressure is then obviously transmitted back to the pump that's providing the flow, and that pump volumetric efficiency goes down. It delivers less flow. So you can see there's a drop off in the inlet flow when it's having to work harder because there's leakage. But what's the good thing here is that the priority port, so the flow actually going to the motor in case of the gritter, you're turning the gritter around, is pretty constant. Okay, so all of this pressure variation and inlet flow variation has all been evened out, and what's happened is that the priority flow has been kept very stable. And it's not magic. What's happened is that the difference between the orange and the blue line is what would be going out of the bypass port, and that simply just goes up and down as the inlet flow goes down, then the bypass flow goes down, and as it recovers, then it goes back up again. And for example, for applications where the bypass flow is then piped back to tank, that doesn't make any difference. And if it is being used for a secondary function, that function isn't critical, then that small change in bypass flow also isn't really an issue. So if we go back to our conveyor belt that we've met earlier on, with some pressure compensated flow control, the sudden decrease or increase of actuator load can cause flow instability. So here we see we're running with a relatively low load of rocks. We suddenly put a large load of rocks on top. What can happen is you can get some instability, often caused by the relief valve suddenly opening and flow going that way, and then closing again and the flow going back to the motor. We can get instability in the circuit itself. So this is with a 2-port valve. If we look at the 3-port valve here, this is the variable priority flow divider again. WebTech offers different damping methods, more extreme damping or less extreme damping to compensate for this very issue, which means that regardless of the amount of load, if you get shock loads onto a motor, then you won't get any of that surging problem. And so Declan's pretty happy with that because, again, he can tick the box for saying he's improved the performance of the machine. And you can see, even with a high load of rocks, it's running stably. Okay, so we're working our way through his 6 challenges, 3 down, 3 to go. So his next challenge is around, as you can see, an awful lot of the valves that we've shown so far have been manually controlled, which is fine when they only need adjustment occasionally. But for some applications, such as the gritter, it'd be quite desirable for the operator to be sitting in the cab. And could we retrofit some kind of remote control so that the cab driver can control the amount of grit coming out the back? So if we look at that application again, if we don't do anything and he just stops the traffic light, stops at the end of the road, If the gritter's just got a constant motor speed, then he's just going to pour a whole lot of grit on the ground. So is there a way that he could automate that? So if we look again at the 3-port valve, the variable priority flow divider, there is an opportunity there to put a motor drive on top of it and have a control box with it, so that you can actually tell it what amount of flow you want at a particular time based on certain characteristics. Take the lid off, you can see there's a motor drive. So now we're feeding in 2 signals. We're saying how much grit do we want, and also what's the speed of the vehicle. As the speed of the vehicle slows down, so does the grit, because we've fed a signal to the remote controlled variable priority flow divider, and it's turned the flow off and fed all the flow to bypass and away from priority. Okay, so we've covered 4. So the next one is, on some of the machines, there's also a need to run an auxiliary function. And as we mentioned before, the advantage of a 3-port valve is that bypass flow could be used then for something else. And so if we look at a screening machine or a recycling machine, and on the right-hand side here, we have a monoblock valve, which is a combination of a variable priority flow divider, a directional control valve, and a relief valve. And then the opportunity here to go to high pressure carryover, so you could put these in series and then have another relief valve protecting the next valve. So we've got the inlet flow coming in here, going through the variable priority flow divider, and then we select whether we want to run circuit A or B. We just do that. You can see we're running the conveyor in the middle there, which is highlighted in yellow. If we move the lever across, we can see we're running the conveyor on the right. The system could be configured differently, so that we've got a conveyor and tracking, and we could switch between the conveyor and the advantage here is that this is embodying all of the characteristics, all the great characteristics of a variable priority flow divider, and then combining it with a directional control. So we still have that consistency of flow, so it's pressure compensated, and we have the bypass flow, and we have the relief valve in there as well. Okay, so on to the last of Declan's challenges, and that is that if we've got an auxiliary flow, another application could be to actually move some cylinders. And if I've got 2 cylinders, how do we make sure that we get the 2 cylinders to go up together? One of the challenges you've got on some of the machines, that's not working very well. So if we look at this example, here we have the pump delivering the flow to the 3-port variable priority flow divider. We've got the relief valve going back to tank here. So the main flow across the top is driving the motor drive, which is moving the conveyor that we've already seen. And then the bypass flow is going to a directional control valve, which can then be switched to move these 2 cylinders. And for the eagle-eyed amongst you, you can see that maybe this isn't going to work that well. We've got an uneven load. So indeed, as we lift up the cylinders, see that they've gone up a bit crooked. They reach the end of stroke, and then they catch up. But during that time while they're going up, everything's a bit uneven and is likely to buckle or jam, and that's really not the solution that Declan wants. That's not great engineering practice to do that. So one of the valves that Declan's looking at is the flow divider combiner. And so here we've got the flow coming in the center, going across these 2 hook spools, and then going out of ports A and B. And there's the symbol for it on the left. So here we can see that the pressure on A is higher than the pressure on B. And that because the pressure on B is lower, if these weren't compensating, you would see more flow going across from P to B rather than P to A, and you get an unequalness in the what's supposed to be a 50-50 split. But because these spools are compensating, you can see here that this spool here is aligned perfectly. This is then compensating to make up for that difference in pressure drop. Equally, in the other direction, and the flow comes back down again from a cylinder. Here we can see that the flow through A is higher than the flow. Sorry, the pressure at A is higher than the pressure at B. And again, we can see the spools compensated to make sure that they retract at the same speed. So if we look at the same circuits we looked at before, everything's the same on the left-hand side. All that's changed is we've now introduced this flow divider combiner here that feeds into these two cylinders. Now move the directional control valve across, we can see that the two cylinders go up equally. And if we were then to move it back, we can see that they retract equally and then combine together through the FDC. And just a note on this valve here is a rotary shear valve, zero leak rotary shear valve. One of the functions that isn't entirely obvious, you might think it's just you switch it on or you switch it off, is that there is an interflow capability. So you can move the handle to half position and you get effectively half flow. You move the handle the whole way, you get full flow, and then the same in reverse. So half flow and back to neutral. Okay, so that takes us through all 6 of the challenges that Declan had. He's now found solutions to them. So the system is running cooler thanks to a 3-port flow control valve or flow divider. He's replaced 2 valves with 1 by having a built-in relief valve. He stopped the juddering and surging, both through thanks to the pressure compensation and the damping within the valve. He's added remote control, electric actuation. That could be with a milliamp or volt signal, or it could be with a CAN signal. He's controlled an auxiliary lift using a directional control valve that could be built in, and also using the bypass flow from the 3-port valve. And then that auxiliary flow he's then split evenly using a flow divider combiner. So that takes us really to the end of Declan's challenge. Lauren's happy because Declan has now successfully reduced the running costs. He's reduced the wasted heat. He's saved on diesel. He's got better performance on the machines. So Lauren's happy. Declan's proud that he's managed to design a That's a little overview of the different valves we've talked about over the last hour. So the monoblock valve with directional control, the 2-port pressure compensated flow control, the variable priority flow divider with motor drive, the flow divider combiner, and then the sort of standard variable priority flow dividers. One of the things that we mentioned right at the beginning is what sets WebTech apart is that we are flexible, we are adaptable, and we have made hundreds of different variations of these valves depending on people's applications, and taken a feature from one valve and tried perhaps to combine it with a feature from another valve or branded it differently in order to really meet the requirements of that customer and that application. And that's been through the use of our Make It Blue 4-step process. So that brings us to the end of the presentation. I hope you've enjoyed that, what we've shown you today and how Declan's made some savings there. If you want some more information, feel free to go to our website. If you scan that QR code, it will take you straight to the flow control valve section on the website. If you'd like to ask any questions to us, you can email us on sales-uk@webtech.com, or you can contact our local WebTech distributor, or indeed, if you've got any questions, then we're open to questions now.
Thanks, Mike. Thanks for that. There was one question. This was a little bit earlier, and the question is, why is the compensator behind the orifice? Mostly it's before. I can't remember the exact point of that, where that question was, but it was, I think it was when you were talking about the VFDs in the first example.
Probably the VFC, right?
Could well have been, yeah.
Let's see if we can just quickly go.
It was during the VFC portion.
Yeah. Thanks, Matt.
Yep.
try and get to that. There we go. I couldn't tell you exactly why it's designed like that, but the compensator is effectively moving inside this section here. So this section in light grey is moving inside the section in dark grey. Exactly how we came up with the design, I'm afraid I can't tell you, but it works well.
Okay, thanks for that. There was nothing else in the chat, unless anyone else has got anything to ask now. Feel free to unmute yourself. Thank you. You're welcome. Otherwise, if not, then we can leave it there. As Martin said, there's the QR code that will take you to the website. I will send. Yes, Mark.
There's another sort of question in the chat. What are the available voltage options for a VFD and ME series?
Thank you, Mark. I changed screens. Thank you.
Off the top of my head, I'm going to look to one of my other WebTech colleagues to answer that. I've got a feeling it's 24 volt in order to drive the motor, and there may be a 48 volt option, but I would need someone else to verify that. Perhaps if you
Jonathan, I can send you the data sheet for that.
we've got your email address. We can send the data sheet.
You have the potentiometer. You have the 0.5 to 5 volt DC or a 4 to 20 milliamp.
Yeah, that for the control signal, and the actual motor drive itself, I think, needs to be fed about 24 volts, 12 or 24, I think.
Okay, perfect. I appreciate that. Yeah, if not, I'll just look into the technical data sheets that are available on WebTech.
Yeah.
Great. Okay.
I can get you a link to that. No problem.
Gotcha.
If you're talking power supply, it's 11 to 28 VDC.
There you go.
Okay. Gotcha. Thank you.
Yep.
Welcome. Yeah, so I will, send around. Well, the recording will go out within about half an hour of this. I'm also going to put together a quick survey. If you could, it'll be a quick sort of 5 to 6, 7 questions. It really helps us, like anyone, if you can fill these in, so we can try and improve on the next one. I'll send that round with some. Also, I'll stick some links to some other resources we have, i.e., some of the data sheets or links to the product pages, and I'll do that probably this afternoon. If not, it'll be tomorrow. And with that, thank you very much. So appreciate your time, and hopefully we can join us on the next one. But keep a lookout in your email for some more. So thank you, and have a good afternoon.
Thanks, everybody. Bye-bye.
Thanks, Martin. Thanks, Sam.